All right, let's go ahead and get started. So we finished off pretty close to this slide where we were talking about these two things, and these two things being dBn and dBu, and what are they? They are bases. More specifically, what kind of bases are they? They are non-nucleophilic bases, and they are soluble in organic solvents. And so you all had an extra credit assignment that was due today in class. So if you want to go ahead and pass them to your right, I'll pick those up and we'll talk about which nitrogen atom is the basic atom in dBn and dBu. So in both of them, I mean, other than the size, the fact that the ring sizes are different, they all have this group. We have a nitrogen that's bound to a carbon, doubly bound to another nitrogen, and then you've got some other stuff that's going on, right, that these rings. So I'm just going to use circles as the rings at the moment because we're talking about either dBn or dBu. Okay? So how would we go about explaining which of these nitrogens is the most basic? Because if you look at it, there's a lone pair of electrons here, and there's a lone pair of electrons on that nitrogen. As I look at them, both of them should be able to function as a Lewis base, right? But when we start to look at resonance structures, I notice that I can draw a resonance structure for this molecule where I can push these electrons like this. Right, and so we have the structure on the left and we have the structure on the right. Given that we can draw that resonance structure, which one would you argue is the most basic nitrogen atom? This one. That's right. That is the one nitrogen atom that can function as the base. So those nitrogens are actually the basic nitrogen, or that nitrogen, excuse me, is actually the basic nitrogen in dBn and dBu. Okay, it can only function as a base at that nitrogen because of resonance structures. So go ahead and click these. Keyshawn, you got yours? Okay. These are really good bases, and they're used industrially quite a bit. Okay, one of the things that students typically gravitate towards is something like potassium tert-butoxide, and it works, but it's a salt, and sometimes it has limited solubilities in the solvents that you're wanting to work with, whereas that's not the case here. And so let's look at a couple of examples where they've actually used this type of chemistry to make things that are useful. So for example, here we have an alkyl halide. It's a bromide. It's a secondary bromide. They treat this with dBn in this particular case. It does an E2 elimination mechanism, puts in a carbon-carbon double bond right where they want it, okay? And then they do a couple of, some dilute acid, some other things. We won't worry about this, but you actually ultimately end up getting to this product here called a prostaglandin. Anybody know what prostaglandins are useful for? Where do you encounter prostaglandins? It is. Anytime you're running a fever, you have inflammation, arthritis, all these types of things are a result of prostaglandin synthesis in your body. Okay, prostaglandins actually are part of a cascade of reactions called the arachidonic acid cascade, which for those of you who are going to go on and study medicine, you'll learn an awful lot about. And if you think the stuff that you're learning in organic chemistry is complicated, the arachidonic acid cascade leads to many, many products. And it would take up more than these 3 boards to go through all of it, okay? A lot more. And so there are groups around the country that study these types of molecules. And you need, this is an example of one called PGA2, but there are many different classes of prostaglandins that are all synthesized through this arachidonic acid cascade. But also, they needed standards of these so that you can identify them, just like you needed standards when you were doing your TLC analysis, right? Chemists need standards to know where things come in certain techniques that they use, and so you have to synthesize these independently. And they actually use sophomore level organic chemistry to do this. This is just an E2 elimination to put the double bond in, and then on treatment with acid, this all ends up becoming the prostaglandin of interest. But you can see the mechanism, right? This electron is being pushed here to form this double bond. This pi bond is actually what functions as the base, abstracts that hydrogen, and so on and so forth. So it's a pretty straightforward reaction, works really, really well. Okay. We know that in an E2 elimination reaction, as we go down a family, the rate of reaction is going to increase, right? Leaving groups get better. That's also the same in an E1 elimination mechanism. We know that the better the leaving group, the faster the reaction, right? Turns out that alkyl fluorides are pretty stable. They don't eliminate HF very readily. That's not to say you can't get it to eliminate, but it just doesn't do it very readily. Iodides eliminate very, very quickly and are hard to keep around, actually. Bromides and chlorides are typically what people work with, just because of the ease of working with them, generating them, etc. If you look at the rate of reaction between E2 and SN2, they go in opposite directions. So you'll remember that a primary alkyl halide in an SN2 reaction was really good, whereas a tertiary didn't undergo an SN2 reaction at all. It's exactly the opposite in an elimination, okay? A tertiary alkyl halide can undergo an E2 elimination very, very quickly, okay? A primary is a little slower, okay? And it has to do with the fact that halogen-carbon bond is a little weaker in the tertiary, okay? And so it allows for that reaction to go a little bit quicker, okay? So why is a tertiary alkyl halide not a problem in an E2 elimination? Why is that not a problem? Okay, that's right. It has to get to that carbon, right? What about in an E2? You're on the right track. It doesn't have to attack that carbon. What does it have to attack? A proton, which is small, right? And on the adjacent carbon. And so that's why these seem to go in opposite directions. It's because in the bottom case, our Lewis base is acting as a base. In the top case, our Lewis base is acting as a nucleophile. And that's why you see this go in opposite directions. Okay? So, for example, if you look at a primary alkyl halide, and just hydroxide here functioning as the base, you can get the elimination. Notice what type of alkene we get. We get a monosubstituted alkene. Whereas when we're reacting with a tertiary alkyl halide, we get in this particular case, we get a disubstituted alkene. So which one's more stable? The disubstituted. Remember, the more substituents you add to an alkene functional group, the more stable that alkene, right? And so if we're going to stabilize that product, what does it do to the transition state? It lowers the energy, right? So it's the Hammond postulate all over again. And so if we lower that transition state energy, what else are we lowering? So from starting material to transition state is also called what? The energy of activation, or the activation energy. That's right. And if I lower that energy of activation, what happens to the rate of my reaction? It increases, right? So that explains why a tertiary alkyl halide actually can react much faster than a primary alkyl halide because of the stability of the products, okay? And so that lowers that energy of activation, and you end up with a much faster reaction. So today we're going to continue talking about E2 elimination. We're going to talk about a rule that you need to commit to memory, and that's Zaitsevs Rule. I spell it with a Z. There are some books that spell it with an S. We'll see those spellings here in just a moment. It's the same thing. We're going to talk about Zaitsevs Rule. I hope that we can get into the E1 and the stereochemistry of elimination reactions, but if not, we'll save that for Wednesday before our inverted lecture. So, if we look at this example, here we have what kind of alkyl halide? That is a secondary alkyl halide. We've got a base. In this case, it's triethylamine. Okay, so it's just an amine. Nitrogen has a lone pair of electrons. It's not shown. This allows for a elimination to occur. This is an E2 elimination. And there are some things that characterize an E2 elimination that we've already kind of talked about, right? We know that the kinetics are going to be second order. So in this particular reaction that we have drawn up here, the rate of the reaction is going to be dependent on the concentration of what two species? Okay, so the base and the alkyl halide, right? So if Jack wants to speed his reaction up a lot and get out early, right, he's going to double the concentration of the alkyl halide and he'll make double the concentration of the base, in which case his reaction rate will go up by 4, right? So that's pretty significant. We know that the mechanism is one step, right? This undergoes a single step reaction where the nitrogen atom will abstract the hydrogen and we end up with the product through one step. We know that the more substituted halides react the fastest, so tertiary much faster than secondary, much faster than primary. We know this is favored by strong bases. The stronger the base, the faster the reaction. We know that the leaving group matters. We know that bromide will be much better than a chloride, right? And we know that solvent matters. We know that it's going to be favored by polar aprotic solvents, okay? Why does the solvent matter here? If kaolin did this reaction in, say, THF, why would that go faster than if she did the reaction in, let's say, ethanol, an alcohol? Why would that matter here? What can't THF do that alcohols are doing? They're hydrogen bonding, right? And what would that alcohol be hydrogen bonding with other than itself? The base, right? Nitrogen has a lone pair of electrons, and that alcohol will form a hydrogen bond with that nitrogen. And so you'll end up with alcohol around the base or around that electron pair, right? Can it function as a good base when it's coated with something? No, right? And so that all has to get stripped away before it can function as the base. But in THF, tetrahydrofuran, there is no, it's polar, but there's no, it's somewhat polar, but there's no hydrogen bonding that can take place with THF, right? It just has a dipole. And so it can't form a strong hydrogen bond with the nitrogen of the amine. And so we would expect that reaction to go much faster, okay? So let's do a quick concept test. Rank those following in order of increasing reactivity, least reactive to most reactive, in terms of an E2 elimination, all using the same base. And let's just call them from left to right, A, B, and C, which I should have put up there. So which one of these is going to be the least reactive? The first one, A. Which one's going to be the next most reactive? C is going to be the next most reactive, right? Because we're going from primary to what kind of alkyl halide now? Secondary. And then, of course, the most reactive is going to be that tertiary alkyl halide. Now, I made this one relatively easy because the leaving group is the same in all cases, right? But I could have put up there different leaving groups and different substitutions, and you would have had to have made an argument, right? You know that primary is slow, you know that tertiary is fast, secondary is going to be where you have to make that argument, usually, okay? And you know that iodides are much more reactive than bromides, are much more reactive than chlorides. So you'd have to kind of weigh the pros and the cons, because you know that the leaving group also matters in this reaction, okay? So here's a couple other examples of using eliminations that you learned about as a sophomore to do real things with. So for example, starting with this molecule, right? What kind of alkyl halide is it? It's primary. We're going to do an E2 elimination. We're going to get this alkene. What's DMSO? DMSO? It's a polar aprotic. It's a polar aprotic solvent, right? It's a pretty good polar aprotic solvent. It dissolves salts as well as organic molecules, and so quite frequently when you see potassium terbutoxide, people will use DMSO as the solvent. It is my least favorite solvent to use, to be quite honest with you, because it's so high boiling, it's hard to get rid of when you're done with the chemistry, but it's still, industrially, it's kind of useful. Notice we get the alkene right between the alpha and the beta carbons. We get this primary, or this monosubstituted alkene. And then through several steps, they were able to convert this molecule into quinine, which is an anti-malarial drug, right? So if you live in a country that is prone to malaria, they quite frequently lace water with quinine, and you can have a way to help fight off malaria. Now, this molecule is interesting for another reason. We've got a base, right? How many equivalents of base do you think we need for this reaction to occur with this particular molecule? By equivalents, I mean if we have 1 mole of this, how many moles of this do you think we need? In all the chemistry that we've talked about so far, we've needed 1 mole of base, right? 1 mole of base reacts with 1 mole of alkyl halide to give 1 mole of alkene. But that's not the case here. Why? Actually, you need 2. You need 2 for this reaction to go as written. Why? What other functional group is in that molecule that will react with the base? What kind of carboxyl group? That's a carboxylic acid. Carboxylic acids will react with the base first and make a salt. So you need a base to do that, and then you need an equivalent of base to do the actual elimination chemistry. So one has to pay attention to other functional groups that can react with bases as well. Here's an example where, again, we have a carboxylic acid, right? We've got a ketone. We've got a primary alkyl iodide. They use DBU. How many equivalents do you think we need? 2, right? So you'd need 2 equivalents. You get the elimination to occur, and then through several steps, you actually build estradiol, which is a female sex hormone. And so you can see these rings right here are this part of the molecule, but you need this and this to build up the rest of it. And so this is how they were synthesizing these types of molecules back in the day. Now, we need to talk a little bit about this rule called Zaitsevs Rule, and you'll see it spelt both ways, with a Z and with an S. Some textbooks use S-A-Y-T-Z-E-F-F. I don't know which one's correct. All I know is that this is the one that I use, because Zaitsev sounds like it should start with a Z to me, okay? And so that's the one that I use all the time when we're talking about this. Now, when we're looking at an elimination, so here we have a tertiary alkyl iodide. We've got hydroxide. It can't function as a nucleophile because it's a tertiary carbon. It's going to do an elimination. But you'll notice that beta 1 and beta 1, we've got 2 beta 1 carbons. These are identical because there's a mirror plane of symmetry that runs through here. That would yield this product, right? But we could also have a situation where the base may abstract a hydrogen from beta 2 and end up with the disubstituted alkene. What's more stable, a trisubstituted alkene or a disubstituted alkene? Tri. And so this is actually the major product of the reaction, okay? And so we say that this is a Zaitsev alkene because it's actually the more substituted that is formed, okay? Now, the ratio of A to B be hard for you to predict, okay? But I can pretty well guarantee this is going to be better than 80% of the final product. Okay, is this more substituted alkene, this trisubstituted alkene here. Okay, the important thing to know is that Zaitsevs rule works. It's very reliable as long as you're dealing with relatively small bases that aren't particularly bulky. Okay. And you'll even see that times with bulky bases that Zaitsevs rule still holds out, but maybe not to the same ratio. Okay, so with a really small base, this may be 90 to 10, but if we use something like dBu or dBn, maybe it would go down to 70-30. Okay, because the bigger the base gets, the less likely it is to abstract a hydrogen from a more substituted carbon just because of steric hindrance. Okay, so one has to pay attention to that. So if you were to tell your friend what Zaitsevs rule is, how would you describe it to him? I've always described it in layman's terms as the carbon atom with the fewest hydrogens loses the hydrogen. Right? Zaitsevs rule is stealing from the poor and giving to the rich. Okay, the carbon that has the most hydrogens gets to keep its hydrogens. The carbon with the fewest hydrogens loses out. Okay, in this case, beta 1 and beta 1 have how many hydrogens on them? 2, and beta 2 has 3, right? So one of these beta 1 carbons is actually going to lose a hydrogen to give the major product, okay? But it's all about alkene stability. Okay, it's about product stability. And so if we look at this example, here we have 2-bromo-2-methylbutane. What kind of alkyl halide is this? It is tertiary, so it's going to be pretty quick, right? We've got 2 methyl groups, which they've labeled as beta 1, and then we've got a methylene group, which they've labeled as beta 2, right? And if you look at this, this is what the transition state sort of looks like for removal of a hydrogen from one of the beta 1 carbons, okay? What are all these dashed lines telling us again? Please refresh my memory. They're what? Okay, we've got a process of making and breaking going on. So this is telling me that I'm starting to make a bond between this oxygen and this hydrogen, right? This is telling me what? I'm starting to break the carbon-hydrogen bond, and what does this one tell me? I'm starting to form the what bond? The pi bond, right? We have to be a little more specific there because the double bond actually has a sigma and a pi. The sigma's already there. And this tells me that the leaving group is starting to leave. Right? All this is happening at one time, right? Why is this transition state less stable than this transition state? What is the transition state starting to look like? Is it starting to look like an alkene or an alkane? Or, I mean, an alkyl halide? Does the transition state look more like an alkyl halide or more like an alkene? It's starting to look more like an alkene, right? And what do we know about alkene stability? The more substituted it is, the more stable. So if this transition state is starting to look like an alkene, and this is starting to look like what kind of substituted alkene? And this one's starting to look more like a, and so this is more stable, right? So what's that going to do to the transition state energy? It's going to lower it. And if I lower the energy of activation, I speed up that reaction, right? So this reaction, where we abstract a hydrogen from beta 2, is actually faster than abstracting a hydrogen from beta 1. And that doesn't seem intuitive, because you would go, well, beta 1, if you look at both beta 1s, that's 6 total hydrogens that that base has chances of running into and deprotonating. Whereas for beta 2, there's only 2 hydrogens. So that's a 3-to-1 ratio. You would expect, just based on statistics, that this would actually be the major product based on a statistical analysis. But it's not statistics, okay? It's all about product stability and the transition state energy, okay, or the energy of activation. And so this ends up being the major product. And in fact, if you were to run this reaction as shown, both of these are pretty volatile. They're kind of gases. They're hard to analyze. But if you did this reaction and ran this through, I don't know, let's say like a gas chromatograph. Y'all done the GC lab yet? Not yet? You will soon. These could be separated on a gas chromatograph, just kind of like on a TLC, and you can get information, you would find that this would actually be, maybe 90% of the mixture, and this may be somewhere around 10, maybe even 5% of the mixture. Okay. Here we have a situation where we have two aromatic rings. We have a carbon atom with a bromine, so we got an alkyl bromide, right? But we've also got these other functional groups. We're using a reasonably good base. And here we have two possibilities, right? We can get the transalkene or we can get the cisalkene. And we find that the transalkene is the majority product in this elimination. Why is that? Why is it the major product? It is more stable. Why is it more stable? Those groups are farther away from one another, right? Has nothing to do with conjugation or resonance structures, because I can draw just as many resonance structures for this molecule as I can this one, okay? But the two big groups are as far apart as possible, okay? These two aromatic rings actually start to crowd out and start to bend the alkene a little bit. Do you think an alkene likes to be bent? No, it doesn't like that, right? And so forming the cisalkene through these types of eliminations, this is actually a minor product. I've done this exact reaction before, and I can tell you that at least when I did the reaction, I could just barely detect that any of this was present. Okay, I mean, it's pretty good in giving the transalkene product in very high yield, okay? And so we would say that this reaction is stereoselective, okay? Starting from this, we get predominantly one stereoisomer, in this case the trans. And so when you have a reaction that predominantly gives you one stereoisomer over the other, we say that those reactions are stereoselective, okay? Stereoselectivity and enantioselectivity, which is another type of stereoselectivity, are king when it comes to industrial organic chemistry these days. You would not want a reaction that gives you a mixture of things, because you have to separate them, and then some of it is not what you want. You got to throw it away, and it's very wasteful. So industries are very, very interested in, can you make things in a stereoselective fashion? Okay. So another quick little concepts test. What is the major alkene product produced by the elimination of the following? When we think about these eliminations, the first thing you want to do is identify where the alpha carbon is. On the one that I've drawn, where's the alpha carbon? It's the one bearing the halogen. Everything that's attached to that is a beta carbon. So I've got beta and I've got beta prime. I've got two different beta carbons. According to Zaitsevs Rule, which one of those carbons should lose its hydrogen? Beta prime. And so we would predict that the alkene product would be that as the major product. Same exercise here. So we've got chlorine and what did I put? There we go. So the first thing I do is I find the alpha carbon. It's the one bearing the chlorine. And how many beta carbons do I have now? I have 3, and they are all unique, aren't they? So I'm going to label beta, beta prime, beta double prime. You can use whatever numbering system you want. I don't care. Okay? Which one of those would Zaitsevs rule predict to be resulting in the major product? Beta double prime. Yep. Only one hydrogen there, right? Two hydrogens there, three hydrogens there. Yes, sir.
What would you do if your betas weren't unique?
If they're not unique, then you have some type of mirror symmetry, and it wouldn't matter which one then, right? So, for example, if I had another methyl group there, these would be identical. And it wouldn't matter whether it was lost here or here. It would give the same product. Now, what you might be getting to is something like this, where, let's say we have something like that. Now, all beta carbons are different, but beta prime and beta double prime have the same number of hydrogens, right? So what would Zaitsevs rule tell us there?
It would form whichever one would make a more stable sands or trans or cis.
Okay, that's not necessarily a bad thought, but that's not possible here because of the 5-membered ring. It's going to be locked into that cis conformation. Can't be anything else. If I eliminate this hydrogen, I end up with a tetrasubstituted alkene. If I eliminate this hydrogen, I end up with a tetrasubstituted alkene. Your argument would be that you would get predominantly tetrasubstituted alkene, but it would be a mixture of this isomer and that isomer. And given that this is a pretty small group and this is a pretty small group, maybe 50-50. Okay? So Zaitsevs rule basically just tells us which hydrogen gets lost, but we can have situations where those numbers are identical but would lead to different alkenes. And Zaitsevs rule does a pretty bad job of predicting then which one would be the major. Okay? And we'd have to make an argument based on what we know. Okay? Let's talk a little bit about E1 elimination. So E2 is dependent on both the alkyl halide and the base. It is favored by polar aprotic solvents. It and SN2 chemistry are fairly similar. So E1 should be very similar to what kind of chemistry? SN1. So what favors SN1 chemistry? Polar aprotic solvents, weaker bases or weaker nucleophiles, right? Okay. So all the things that you learned about for SN1 are going to be relevant here in E1. So for example, if you took tert-butyl chloride and you reacted it with water, right? This is kind of along the lines of what we did in our experiment in our demonstration, right? And in that case, we did SN1 chemistry. In this case, they're talking about doing E1 chemistry. So how do I know that the stuff that I did in the demonstration went SN1 and not E1? In both cases, the color would have changed from pink to colorless because in both of these, you're going to eliminate HCl, right? So how was I confident in telling you that we got alcohols instead of alkenes in those reactions that I did in the demonstration? Oh, it did act as a nucleophile, that's right. But how am I confident about that? How do I know, how did I know to tell you that it gave the alcohol and not the alkene? One is a rule of thumb and the other is an observation. The observation was, when we were doing the demonstration, did you see the solution kind of look like it was boiling, releasing a bunch of gas? No. This alkene is a gas at room temperature. If it was undergoing an elimination reaction, I would have seen a lot of bubbles of gas. I saw none. Okay? At least nothing significant. Okay? The other thing is the rule of thumb. In an E1 reaction, if you want the elimination to be the predominant thing that happens, heat it. Heating a reaction favors elimination over substitution in E1 versus SN1 chemistry. Okay? Heating the reaction will favor the elimination. Okay? So quite frequently what you would see, if I wanted this to undergo an E1 elimination reaction, I would have taken the alkyl halide, the water, and I would have put it in a warm bath of something, elevated its temperature to try to force it to undergo the elimination. Okay? So that's a general rule of thumb. We know that the reaction kinetics are going to be first order. It's going to be dependent only on the concentration of the alkyl halide. Water is not a good base, right? How many steps is this going to have? It's going to have two. It's going to form a carbocation. The first step in both an E1 and SN1 reaction is identical. It's absolutely identical. Okay? The leaving group leaves, and you end up with a carbocation. Now, at low temperatures, water will function as a nucleophile and attack the carbon atom and give the alcohol. But at elevated temperatures, water will attack and function as a base and abstract a hydrogen from a beta carbon and give you the alkene. Okay? That's where the difference comes in. The first step is identical in an SN1 and an E1 reaction. It's the second step that's different. Okay? And they have different energies of activation, and so by giving it more energy, I can favor one over the other a little better. Okay? Looks just like an SN1 energy profile, right? Okay? You'll notice on the y-axis is energy. On the x-axis is the reaction coordinate. We've got our alkyl halide. We've got our product. We go through the first transition state. We get the carbocation intermediate. That then undergoes the elimination with an energy of activation, and we end up with the products. Okay? Draw it out exactly the same. The only difference is the product that you're going to put here. Okay? We know that the E1 reaction is going to be favored by tertiary alkyl halides, just like an E2 elimination is. So the more substituted the alkyl halide, the faster the reaction. But the reason is different here. The reason that a tertiary alkyl halide reacts faster is because a tertiary carbocation is more stable. We've talked about that before, right? The more stable the carbocation, that lowers that energy of activation, that speeds up the rate of reaction. Okay? And so we know that tertiary alkyl halides will react faster than secondary alkyl halides. Primary alkyl halides do not do E1 chemistry because a primary carbocation is not stable. Okay? And so these will only undergo E2 type eliminations, whereas these can do both E1 and E2 eliminations. Okay? But if we're using a polar protic solvent and we're using a weak base, chances are it's going to be a E1 elimination. Okay? Zaitsevs rule also applies to E1 reactions, just like they apply to E2. Okay? So in this case, we have two different beta carbons. We're using just a different base. We're using water. We're going to heat it up. We'll find out that the tri-substituted alkene is the most, or is the predominant product in the mixture. Okay? And so we've really already kind of talked about this. I won't spend too much time on it, right? In both cases, the first step is identical. You generate a carbocation. The difference, in an SN1 reaction, the nucleophile attacks the carbon. whereas in an elimination, it functions as a base and goes after the proton. Temperature matters here. If you run this at room temperature below, bet on SN1. If it's above room temperature, bet on E1. Okay? Elimination and substitution always compete with each other. You cannot have a perfect SN1 reaction most of the time, unless there's no hydrogens to eliminate, and that's possible. Okay? But if there's hydrogens on beta carbons that you could eliminate, you almost always end up with a little bit of E1 product if you're trying to do an SN1, and you almost always end up with a little SN1 product if you're trying to do an elimination. Okay? But you can favor one or the other by controlling the temperature and the conditions.
What's the best way to tell whether or not it's mono, di, tri, or tetrasubstituted?
Are you talking about the alkene?
Yes.
You look at the 2 carbons of the alkene and you ask yourself how many carbons are attached to that alkene.
Okay.
So if it's 1, it's mono, 2, it's di, 3, tri, and 4, tetra. Stereochemistry matters in these elimination reactions. Not all hydrogens are capable of being eliminated, even if they're on a beta carbon. Okay? And it turns out that when the hydrogen and the halogen are on the same side of the plane, we call these syn-periplanar. This hydrogen would not undergo an E2 elimination with that halogen. The hydrogen and the halogen have to actually be anti-periplanar to one another. And we've already talked a little bit about this last week. Why is it that the hydrogen and the halogen have to be anti-periplanar to one another? There were 2 reasons that you all came up with. Both of them were good. Give me one of them. Okay. So if I'm thinking about the base coming in and abstracting this hydrogen, right? These electrons are going to become the pi electrons, right? They have to come over and form that pi bond and push the halogen out. So if you want to think of it, these electrons are kind of like the nucleophile coming in and making the leaving group leave, right? So that would dictate that these 2 things have to be on opposite sides of the plane, or anti-periplanar. The other perfectly good rationale that you all came up with is a base has what on it? All bases have what? A lone pair of electrons. These halogens have what around them that aren't shown? Electrons. So if the base tried to come in from this side to abstract this hydrogen, it would be interfering with these other electron pairs. And what do we know about electron pair, electron pair? They repel. You learned about that in Vesper theory, right? So it makes sense from a repulsion point of view, but it also makes sense from a geometry point of view of how that leaving group has to leave. Okay? So we need to have the hydrogen and the halogen anti-periplanar to one another. And that's all fine and well as long as all you have is sigma bonds and it's acyclic. When you start to put something in a ring, it becomes much more difficult. So if we look at this example, right? Here we have chlorocyclohexane. We know that chlorine being the big group, it prefers to be equatorial, right? We learned that. But we also know that we can undergo ring flipping, right? Or chair-to-chair interconversions. Which one of those is responsible for the elimination chemistry? It turns out it's actually the least stable conformation. Because when I look at this, I can see that the halogen and the hydrogen are anti-periplanar to one another. When this is in the equatorial position, which is the most stable chair conformation, none of the hydrogens are anti-periplanar to that halogen, and that makes a difference. Okay? All right, I've got a bunch of stuff I need to hand back to you. I've got an inverted lecture in the exam, so don't leave until you get everything back. Kaylin. I will be in my office this evening from 5 to 6 if you want to come by and pick up your exam to redo.